Okay, let's unpack this. Imagine, right, a robot needing to follow you through somewhere really chaotic, like a busy train station, or maybe a factory floor.
Yeah.
Doesn't just see you once. It has to keep track of specifically you with all the other people moving around, all the obstacles, and then it needs to figure out how to actually move to stay with you.
hmm
How does a robot even begin to do that reliably, in the real world?
That incredibly difficult challenge is exactly what we're diving into today. It's called embodied visual tracking, or EVT.
EVT.
Yeah, it's part of embodied AI.
Right.
And it's absolutely fundamental if you want robots operating not just in the real world, but like interacting with it dynamically.
And the sources we're looking at, they really highlight the core difficulty here. It sounds like EVT needs two big things working perfectly together almost at the same time.
Exactly. First, the robot has to accurately recognize the specific target. So identify you based on maybe a description like the person with the bright green backpack.
Okay, recognition. Got it.
And second, it has to plan its own movements, its trajectory, basically, to follow you without, getting lost or stuck or bumping into things.
Recognition and planning. But the sources say the usual way is to treat those separately.
That's the standard approach, yeah. The papers point out you often have one module just for finding and recognizing the target, like a detection model.
Mm.
And then a totally different module handles the navigation, the path planning, maybe using reinforcement learning or something like imitation learning.
And that separation, that's where the trouble starts. The paper mentions error accumulation.
Precisely. If the recognition system is off by just a little bit, maybe it loses track for a second or thinks someone else is the target, that bad info gets fed to the planning system.
Which then plans a path based on, well, wrong information.
Right. Or even if recognition is perfect, the planning part is slow or clumsy, the robot falls behind or gets stuck anyway. It's like these two systems, they just can't coordinate tightly enough when they're developed independently.
Trying to glue them together after the fact doesn't really work for something this dynamic.
Exactly. It makes it incredibly hard for the robot to really master that complex interplay you need for robust real-world tracking.
Okay, so that sets up the problem pretty clearly. Now, our main source today introduces a different idea, something called TrackVLA.
TrackVLA, yes. And our mission here in this deep dive is to cut through the technical details in these sources and really get at the core innovation. How does TrackVLA try to overcome that recognition planning split?
And crucially, how well does it actually work? What do the results tell us, especially when things get messy, like in the real world?
Exactly. This deep dive is for you, the listener, to give you those key insights without you needing to wade through, all the jargon or the, 1.7 million data samples yourself.
1.7 million. Wow. Okay, let's get into it then. You mentioned the core problem is recognition versus planning. Why is doing both together in a dynamic place so much harder?
Well, the sources really emphasize things like severe occlusion.
Where the target is hidden.
Yeah, constantly hidden by stuff or other people. And high scene dynamics, everything around the robot and the target is moving, changing all the time. A separate recognition system might just lose the target when it's hidden.
And by the time the planning system gets the update and reacts, the whole situation's different.
Exactly. It's that constant need to reacquire, adapt the plan based on this like nonstop visual stream.
Mm-hmm.
And like you said, the typical method keeps detection and planning in their own silos.
Leading to that error buildup, the detection knows what and where now. The planning decides how to move next.
But the planning isn't deeply connected to the identity or the history of that target. It's not really baked in.
Okay, so the system's almost fighting itself sometimes. How does TrackVLA propose to fix that? This is the aha moment, right?
Absolutely. TrackVLA's core idea, the real innovation presented here, is unifying these tasks. It's built as a vision language action model, a VLA model.
VLA, vision language action.
Meaning it learns the synergy, the connection between recognizing the target and generating the robot's actions to follow it. It's not two separate brains. It's one integrated system handling both parts.
One system doing both recognition and planning?
Yeah.
How does that actually work? They seem like really different jobs.
The key is using a shared large language model, an LLM, as the sort of central backbone. Both tasks, figuring out who the target is and deciding how to move to it, they share the same underlying token processing, the same LLM architecture.
Okay. So how does it know which job to do?
It's just about how the LLM's output is interpreted. For recognition,
Hmm.
say, answering a question about the target or describing them.
Yeah.
It uses a standard language modeling head. It just outputs text, like any other LM. It might say, the person is wearing a yellow hat,
Yeah.
or yes, that's the target.
Okay, standard LLM output for recognition.
Yeah.
And for the robot's movements.
The planning.
For planning, it uses a specialized action model that's connected to that same LLM. In this case, it's something called an anchor-based diffusion model. Anchor-based diffusion. We'll come back to that.
Right. But this model takes the LLM's internal state
Yeah.
and decodes it into a sequence of waypoints, basically the path the robot should take.
And the really crucial part the sources emphasize is that these two capabilities, recognition and planning, are trained together.
Yes. Joint training, optimized for that tight coupling. Knowing who to follow deeply informs how to follow them, and maybe even vice versa in some ways.
That makes sense. It learns how the recognition context directly feeds into the planning decisions.
Precisely.
Okay, let's dive a bit deeper into the architecture then. The sources give some specifics. What are the key bits and pieces making this unified system tick?
Well, it starts, naturally, with a vision encoder. They mention using EVA SLA-P, which processes the robot's camera feed frame by frame.
And it's seeing video over time, right? How does it handle all that visual data without getting bogged down?
They use a pretty clever grid pooling strategy. It looks at the very latest frame with lots of detail, fine-grained pooling, but for the older frames in its memory.
It's history.
Yeah, its recent history, it uses coarser pooling. The sources say they used a sliding window of 32 frames, so it gets that historical context without being totally overwhelmed by raw pixels from the past.
32 frames of context, okay.
Right.
And these visual features, they get fed into the LLM.
That's right, through something called a cross-modality projector. It basically translates the visual information into a format the LLM can understand into its latent space.
And the LLM itself?
They used Vicuna 7B in their setup.
Yeah.
It processes these visual tokens alongside any language instructions like the target description, green backpack, and also a special track token that tells it whether it's supposed to be tracking or doing recognition right now.
Got it. Now, that action model you mentioned earlier, the anchor-based diffusion model for planning the path, that sounds complex. What's the anchor-based part about? Why is that important?
Yeah, this is a really neat detail they highlight. So normal diffusion models for generating something like a trajectory often start from pure random noise.
Right, and they gradually refine it.
Exactly. But this anchor-based approach doesn't start from pure noise. It starts from predefined trajectory anchors. Think of these anchors as like a library of common, successful path shapes or patterns that they learn from the training data.
So instead of inventing a path from absolute scratch every single time.
It picks a good starting guess from this library of anchors and then refines that.
Okay, that sounds much more efficient.
It is. The sources report that using these anchors drastically cuts down the number of denoising steps needed to get a good trajectory. And this is where the speed boost comes from.
How much faster are we talking?
While a typical diffusion policy might need, quite a few steps, TrackVLA reportedly needs only 2 denoising steps when it's actually running during inference.
Just 2 steps. That's incredibly fast for diffusion. What's the impact?
It means much faster trajectory generation. The paper claims a 5x speedup compared to a vanilla diffusion approach without anchors. For a robot that needs to react in real time, that kind of speed is absolutely critical. It's a major technical win they focus on.
Okay, so a unified architecture, clever components like the anchor-based diffusion for speed and synergy. But, with any AI model, the training data is everything.
Absolutely.
Yeah.
And they really went big on the data here. The sources specify 1.7 million samples in total for training.
1.7 million samples. That is a lot of training data.
It really is. And it's strategically split into 2 main types, designed to build up both the tracking and the recognition skills.
Okay, tell us about the first type, the tracking data.
So about half of it, 855,000 samples, is embodied visual tracking EVT data. They collected this using their own custom simulator built on Habitat 3.0.
Habitat, okay.
Yeah, and they created 100 different humanoid avatars and put them into over 800 different scenes. Think homes, offices, diverse environments.
And they didn't just have them wander around. They specifically designed this EVT data to be challenging, right? To target those difficulties you mentioned earlier.
Exactly right. They structured it into different difficulty levels.
Okay.
First, single target tracking, STT. Pretty basic. Follow the person.
Simple enough.
Then, distracted tracking, DT. This gets harder. It needs fine-grained recognition using detailed language, like follow the light-skinned man wearing a black suit and blue tie. You have to really see the details correctly among distractors.
Right, you can't just follow any man in a suit.
And the third type, maybe the hardest, is ambiguity tracking, AT. This is where distractors look identical to the target, so the instruction might be follow the first person you see. The robot has to rely on that initial context and disambiguate carefully.
Wow, okay. That really tests the recognition and memory side of things. So that's the tracking data, about half the total. What's the other half?
The other 855,000 samples are video question answering data, VQA.
VQA, why add that?
It's specifically to give TrackVLA broader, more open-world recognition skills. Not just tracking a specific target, but understanding visual scenes more generally. It includes VQA focused on people describing them, identifying them, even asking if two different people shown are the same person. And it also includes general open-world VQA data drawn from public data sets, just to round out its visual understanding.
And the sources mentioned they experimented and found that this 1.1 ratio, half tracking data, half recognition data, worked best.
Yeah, their ablation studies, where they tested different setups, apparently showed this balance was optimal for the final performance.
So why does this whole data strategy matter for you, the listener?
Well, it shows they didn't just train it to follow dots. They trained it on scenarios explicitly designed to push the limits of both tricky tracking and complex visual recognition in dynamic settings. They were aiming for robustness out there in the wild.
All right, so they built this integrated model, VLA, anchor-based diffusion, trained it on this massive, carefully crafted data set. How did it actually do when they put it to the test?
So they evaluated it pretty thoroughly, both in simulation and then, crucially, in the real world.
Okay, let's start with simulation.
First, they tested it on public benchmark, GIM Unreal CV, and they did it zero shot.
Zero shot meaning?
Meaning the model had never seen data from that specific simulator environment during its training. It's a strong test of how well it generalizes.
Okay, and how did TrackVLA fare zero shot?
Impressively well, according to the paper. It achieved state-of-the-art results on that benchmark. On some of the simpler tasks, following unseen objects, it apparently hit a perfect 100% success rate.
Perfect, wow.
And even on the harder distractor tasks in that benchmark, it significantly outperformed the previous best methods. So that really points to strong generalizability. It can adapt to new environments and targets it wasn't explicitly trained on.
Okay, that's the public benchmark. What about on their own benchmark? The tougher EVT bench with those STT, DT, and AT tasks designed to be hard.
On their own EVT bench, TrackVLA also set a new state-of-the-art across all three difficulty levels when compared against various baselines, including, interestingly, other VLA-based methods.
So it'd be other similar approaches, too.
Yes. Though they do honestly note in the paper that performance naturally drops as you go from the easier STT tasks to the harder DT and AT tasks.
Which makes sense.
It does, and it kind of validates their benchmark design, right? It shows that even for a state-of-the-art model like TrackVLA, those ambiguous situations and fine-grained distinctions are still really challenging.
Okay. Now, you mentioned that VQA data was specifically added for recognition ability. Did they test that separately? How good is it at just, identifying things compared to other big models?
Yes, they did. And this is where the results get really interesting from a practical robotics perspective. The sources report that TrackVLA's recognition accuracy is actually comparable to some very powerful, state-of-the-art large multimodal models. They mention systems using SOM and even GPT-4o.
Comparable accuracy to something like a GPT-4o based system. That's pretty strong. But what about the speed? That's usually the trade-off.
Exactly. And here's the kicker. TrackVLA is massively faster. The paper reports an inference speed of 10 frames per second, 10 FPS, for its recognition tasks.
10 FPS. Okay, how does that compare?
Compared to the GPT-based baseline they tested against, which ran at just 0.1 FPS.
Wait, 0.1 FPS. So TrackVLA, doing my math, roughly 100 times faster at recognition for comparable accuracy.
That's what the paper claims, yes.
Yeah.
100 times faster inference. That speed difference is just huge for a robot that needs to perceive and react in real time.
No kidding.
And they also confirm in the ablation studies that training with that diverse VQA data was key. It boosted the recognition accuracy significantly, by almost 30% according to their numbers. Accuracy is great, but accuracy at speed is what you need for embodied AI.
Absolutely. Okay, simulation results are strong, recognition is fast and accurate. But the ultimate test, always, is the real world. Did TrackVLA make it out of the simulator?
It did. They ran real-world experiments, deploying TrackVLA onto a physical quadruped robot, one of those four-legged ones.
Like Spot, maybe?
Something like that, yeah. And the qualitative results they describe sound pretty good. Strong sim-to-real transfer, model trained purely in simulation, worked effectively in the real world. It handled cluttered environments, even low-light conditions.
Getting crucial.
It maintained that high inference speed, still running at around 10 FPS in the real world.
Okay, that's promising. Did they do any like head-to-head comparisons in the real world?
They did. This is pretty cool. They set up a direct comparison between TrackVLA running on their quadruped robot and a commercial tracking drone, a DJI Flip.
A robot dog versus a drone. Okay, how did they test them?
They designed easy, medium, and hard real-world tracking scenarios, things like varying speeds, obstacles, the target ducking behind things, and they ran each scenario 10 times for both the robot and the drone to get quantitative results.
10 trials each. Okay, how did the robots stack up against the purpose-built tracking drone?
On the easy tasks, both did perfectly. 100% success rate for both, no surprise there.
Okay.
But on the medium tasks, more complex movements, some occlusions TrackVLA on the robot started to pull ahead. It achieved a 90% success rate, while the DJI drone managed 70%.
90 versus 70, interesting. And the hard tasks.
That's where the difference was even clearer. These involved high-speed target motion, frequent and complete occlusions. TrackVLA succeeded 70% of the time. The commercial drone, only 50%.
70% versus 50% on the hard stuff. That's actually really impressive. The general purpose robot running TrackVLA outperformed a dedicated commercial tracking drone when things got really tough.
Yeah, that's pretty
Yeah.
compelling. Real-world validation, yeah. It strongly suggests that this unified approach, combining recognition and planning so tightly, really does lead to more robust performance, especially in those complex, dynamic situations where traditional methods might struggle.
Okay, so the results look good in sim, good in the real world, even against commercial tech. The paper also digs into why it works, right, with ablation studies. What did they find when they took the model apart?
Yeah, the ablations offer some nice insights. One key finding they reinforce is just how effective that anchor-based diffusion action model is.
The path planning part.
Right. It consistently did better than other action models they tried, like simpler MLPs or even a standard vanilla diffusion model. Not just in the final score's success rate, tracking rate, but also in efficiency, confirming that 5x speedup we talked about.
So that specific architectural choice really did pay off.
Definitely seems like it. The ablations also backed up the importance of using historical observations, that sliding window of 32 frames.
As a short-term memory.
Exactly. When they removed that, performance dropped significantly. It shows the model really needs that recent history to handle occlusions or when the target moves quickly. It can't just react to the current frame alone.
Makes sense. Anything highlighted from the data side in the ablations?
Yes, they noted that including those diverse types of human recognition VQA data and also training with random backgrounds mixed in were both important factors in boosting the model's general recognition skills. Basically, seeing lots of different people in lots of different visual contexts helped it get better at identifying the right person later.
Okay. So TrackVLA seems like a strong step forward, unifying these tasks, backed by smart data and architecture choices. But, good research always acknowledges limitations. What did the authors say TrackVLA can't do yet, or where could it be improved?
They're pretty upfront about a couple of key limitations in the current system. First, it relies only on egocentric vision.
Just the robot's own camera view.
Right, which gives it a pretty narrow field of view, typically around 90 degrees or so.
Which means if the target darts off to the side outside that cone, the robot could easily lose them.
Exactly. So they suggest future work could look at integrating wider field of view inputs, maybe panoramic cameras, or even fusing information from multiple cameras to give the robot a more, 360-degree awareness.
Okay, broader vision. What was the second main limitation?
The other point they raise is about the controller. The system currently uses a fairly simple waypoint controller to actually execute the planned path.
It just tries to hit the next waypoint in the sequence.
Pretty much. This might limit how agile the robot can be, or its ability to navigate really tricky terrain compared to using a more sophisticated local motion controller that can react more dynamically to the immediate environment.
So integrating better locomotion control could be another step.
Yeah, they suggest that as an area for future improvement, tying it into more advanced low-level movement capabilities.
Okay. So bringing this all together then, what's the sort of big picture takeaway from this deep dive into TrackVLA?
Well, I think the sources make a really compelling case that TrackVLA is a significant step forward for embodied visual tracking. By managing to successfully unify those historically separate tasks, recognizing the target and planning how to follow it within this single VLA architecture.
And supporting it with that huge tailored data set.
Right. It achieves state-of-the-art results in simulation, and maybe more importantly, shows really robust, really fast performance in the real world, fast enough to outperform a commercial tracking system in the harder scenarios.
The core innovation really feels like that deep synergy, that tight coupling. Recognition and planning aren't just talking to each other. They're like part of the same thought process in the model.
Exactly. Enabled by that unified framework and the training data designed to push both aspects simultaneously. The sources really hammer home the point that just recognizing who the target is and just plotting a path isn't enough for reliable following in the real world.
The understanding of the target, their identity, their appearance, it has to be woven directly into the robot's moment-to-moment action planning.
That seems to be the key insight.
Which leaves us with a pretty provocative thought to end on, doesn't it? We've just discussed a system detailed in these sources that can identify specific individuals from descriptions, persistently track them through complex, crowded places, and do it potentially better than current commercial systems. As these capabilities get better and presumably more widespread in robots out there in public spaces, what are the broader implications? What does it mean when robots can not only see and navigate, but also robustly identify and follow specific people or objects pretty much anywhere?
It certainly opens up a complex landscape of possibilities, both positive and potentially concerning. Definitely something that warrants careful thought and ongoing discussion beyond just the technical aspects.